In example 3, a 1,000-kilogram car, so you can imagine the car having a mass of 1,000 kilograms, is traveling 10 meters per second and is stopped by a brick wall in 1 second. So actually, my apologies. I thought it was a shopping cart. It's a brick wall. So you can imagine this, this car, boom, hitting a brick wall and coming to a stop. A 1,000-kilogram car is traveling 10 meters per second and is stopped by a brick wall, whoops, in 1 second. So it goes from 10 meters per second to 0 in 1 second. Calculate 3 things. A, the initial momentum of the car. B, the impulse delivered by the brick wall. So the brick wall, we're calling the edge of the screen. This brick wall is going to provide an impulse to stop the car. And C, calculate the average force delivered by the brick wall. So let's take a look at the first one, calculating the initial momentum of the car. How much momentum did the car have before it crashed into the brick wall? Well, here's our first line of thinking. The initial momentum is equal to the car's mass times the car's velocity. 1,000 kilograms times 10 meters per second gives us 10,000 kilogram meters per second. Again, those are units of momentum that cannot simplify. So the car comes in with 10,000 kilogram meters per second of momentum before it hits the brick wall. Question 2, how much impulse is delivered by the brick wall? How much is that brick wall going to push back and stop the car? Well, we can use the impulse-momentum relationship. We know that the impulse delivered by the wall is equal to the change in momentum of the car. And we know that the car is coming to a stop. It says it's stopped by a brick wall. So all of this momentum that the car has before it hits the brick wall is going to come to 0 once the wall pushes back on it. So this is going to go from 10,000 to 0. That means the change in momentum is 10,000. So setting impulse equal to a change in momentum means that the impulse is equal to 10,000. So in this case, no calculations necessary. This is just conceptual. Impulse is equal to the car's change in momentum, and its momentum changes from 10,000 to 0 once it hits the brick wall. Okay, thirdly, how much force on average did the brick wall give that car to bring it to a stop? Well, now we're going to highlight on this part, the force, and we're going to solve for force since we know the change in momentum is 10,000, and we actually know the time. We were given the time right here. 1 second is how long it takes for that car to stop. So let's try this. We know that the impulse that the brick wall puts on the car is 10,000 kilogram meters per second. How can we solve for force? Well, let's plug in what we do know. We know that the time is 1 second. And so getting F by itself means we divide both sides by 1 second. Divide this side by 1 second, divide that side by 1 second. 1 second goes away on this side, and we get F all by itself is equal to 10,000 kilogram meters per second. And a kilogram meter per second squared is called a Newton, so we can just call this 10,000 newtons, 10,000 kilogram meters per second squared. So this is our final answer for question C. All right, again, this has been a lesson on how impulse and momentum are related to each other, that impulse equals a change in momentum, and an impulse causes a change in momentum. I hope that this is helpful for you as you work on some of the textbook problems in the Hewitt book.